Okay, good afternoon, and sorry for the small delay. I was coming back from a customer and there was heavy traffic jam, so I was here last minute, but then I was in the wrong room, so now I'm in the right place, I think. So I have prepared a kind of, let's say, overview session. I have titled it Real World Challenge, from Real World Challenge to Quantum Circuit through Algorithmic Reasoning. And I have prepared a couple of, let's say, examples. The first example is on quantum teleportation. The second on quantum support vector machines, and the third one on variational quantum algorithms. And I have applied them in examples within the financial services sector. And you see also the typical use case, ledger migration of a bond. So you migrate a bond from one ledger, you could say, to the other. Credit risk prediction and portfolio optimization. I hope they are inspirational for you, so you can also extend them to other industry sectors. The idea is just to give you some examples of how to apply quantum algorithms in specific use cases. And by the way, the three use cases, they are all very well illustrated in our quantum learning platform. You find here the links, and I will share the slides, of course, so that you have the clickable links. So everything I've been telling is a little bit, is based really on excellent materials that I certainly recommend to be studied by all participants. Perhaps some of you already have been doing so, and it is a repetition. Don't hesitate to ask questions and to go into discussion, of course. And I will start with the first thing, and that is, I have called it a migration of a bond, a biotech bond, but that can be any bond in any industry. And of course, I start here by representing a quantum state. As you know, a quantum state is a linear combination of a ground state and an excited and the excited state. So you have here alpha ket 0 plus beta ket 1. And what we also see, of course, is that the sum of the squares of the exponents is, of course, equal to 1. And you know that the syntax of the coefficients is really important. The semantics is that the alpha square is the probability that you find at the moment of measurement 0, and the square of the beta is the probability that you find on the moment of measurement 1. But we represent here the 0 as defaulting, meaning that for the bond there will be no interest, or even the party who is not able to pay back, let's say, the bond, due to, for instance, bankruptcy or any other reason. And the 1 is representing the repayment, and beta square is as such representing the probability of repayment. And the idea is to migrate the bond from ledger Alice to ledger Bob. It's a kind of quantum teleportation algorithm that we are going to apply. And as you know, why do we need to do so? Because, of course, within quantum algorithms and quantum applications, we want to be able to move a quantum state from one qubit to another, because there is the no cloning theorem, and you can even prove the no cloning theorem with mathematical representation, meaning that it is not possible to copy a quantum state from one qubit to another. Of course, there is an exception. You can easily copy your ground state and your excited state by using the C-NOT gate, but that is not the case for any other state that is not equal to 0 or 1, but a linear combination of both. And this is the quantum teleportation algorithm. Some of you might recognize it. And this quantum teleportation algorithm, I am going to take a look to the reason why it is working and then show you the demo. First of all, it is important to notice that in this quantum teleportation protocol, you could say it starts after the first barrier and it stops before the last barrier. That is the complete protocol that you can apply on any quantum state. And as you can see, Alice and Bob are really entangled with each other using a Bell state. Some call this even the E-bit, the entanglement bit, but you could better say perhaps that they are entangled with each other via the Bell state. After this entanglement, we see that Alice, between the qubit Q and Alice, there is a C0 gate followed by the Hadamard gate. You could say the inverse of the Bell state. And then we see measurements on the qubit Q and the Alice, and depending on the outcome, we will apply an X gate or a Z gate. So this is really based on a dynamic circuit, meaning we are going to measure, and the circuit is not yet, we did not yet stop the calculation. No, with the result of the measurement is used to apply an X gate or a Z gate. And why is this working? So let me explain, and then I will give you the demo. You see that we apply the X and the Z gate, and we can prove in a mathematical way that this is working indeed. And I will do so. So it illustrates how you can think mathematically. But before doing so, I need to repeat some important things. By the way, before doing so, excuse me, we have here a picture of the same teleportation circuit, but in a little bit a different way. I will go back here. So between Alice and Bob, we have here this Hadamard and the C0 gate. This is represented here by the psi plus. Psi plus, as some of you might know, is a shorthand notation of the, let's say, of the Bell state. And then the rest of the circuit is exactly the same. The only thing we see here, we have done a measurement, and when you do not continue in your circuit, you can put the measurement at the end of your qubit, and we measure A and B. And now let me take a look to some important things that you must know before understanding this. First of all, we have the X gate, of course. The X of the NOT gate is converting a 0 in a 1 and a 1 in a 0. If you don't believe it, just use the matrices, because each quantum gate is, of course, a unitary matrix, and each qubit is a column vector. The Z gate is doing nothing on the ground state, but is modifying the sign of the excited state. And then you have the Hadamard gate, which is creating superposition between using 0 and 1. We also call it the plus state, but this is purely a convention. And when we apply it on the 1 state, we get a minus. Also, this is a convention, but of course, it is 0 minus 1 with a coefficient. And this coefficient, of course, is square root 2 divided by 2, because if you square it and you sum it up, you get 1 as a result, because the total probability must be 1. If you don't believe this, you have here the matrix, let's say, calculation that proves this, that this is indeed also correctly working. This is something we need to have in mind, because now, how can you prove that such an algorithm is working? This is not showing how it was invented. This must have been some brilliant people, of course, but here it is shown how you can prove it. You could prove it, and I go back, purely with matrices. Matrix calculations, knowing that if you have matrix, let's say gates working on multiple on qubits, different qubits, you will have a tensor product. If you have a gate working on 1 qubit or multiple gates working on 1 qubit, it is matrix multiplication, the traditional matrix multiplication. Here we do it not with matrices, but rather with, let's say, classical calculations using the tensor product. And as you see, psi 0, when we are at psi 0, we are going to multiply the psi plus state with the alpha 0 plus beta 1. This is a tensor product. Why? Because we talk about different qubits. Then, when you elaborate this, you can replace the psi plus by what you find on the right hand side, and you get the bilinearity of the tensor product over the plus. You know that this is bilinear. You can prove that also in a mathematical way, that this is bilinear, but please accept it now. This is this is for the pure mathematicians. And you get then, when you multiply 0, 0 with the 0, you get, and the 1, 1, you get this result. You know, this is a shorthand notation, 0, 0, 0. In fact, you have there the tensor product of 3 individual qubits. In psi1, what we are going to do is a C0, meaning that if the least significant qubit is 0, we do nothing. That is the case for the alpha situation. For the beta coefficients, we need to change the second qubit, as you can see, because of the C0. Then we apply the Hadamard on the qubit Q0. That means that the 0 becomes plus and the 1 becomes minus. We go to the next foil to continue the calculation. We elaborate the plus and the minus, and you get the next line. And of course, square root 2 multiplied by square root 2 becomes 2. And now we are going to group the different terms in a special way. We take the green ones together, the blue ones, the purple ones, and the red ones. And then you can factorize again. You can bring 0, 0 outside of the parentheses. Same for 0, 1, 1, 0, 1, 1. And you get coefficients, you could say, states that are the coefficients, alpha 0 plus beta 1, alpha 0 minus beta 1, alpha 1 plus beta 0, alpha 1 minus beta 0. But what does that mean? Suppose now that we have alpha 0 plus beta 1. This is exactly the state that we want to teleport. So if we measure 0 and 0 on A and B, we need to do nothing. When we measure 0 and 1, we need to change this sign. So we need to do a Z gate on this, I would say, this coefficient. Yeah, coefficient is not the right word, the leading state, I will say. 1, 0, we see alpha 0 plus beta 0, alpha 1 plus beta 0. So we need to apply an X gate in this case. In case we have alpha 1 minus beta 0, we need to do both X and Z. And that is what we are going to do on the next foil. You see that if we measure 0, 0, we do nothing, the identity gate. If we have a 0, 1, we apply Z, 1, 0, X, 1, 1, ZX. And each time we find the same state of B. So, and that declares why this algorithm is really doing the teleportation. And conditionally, we will apply nothing, I would say, the identity gate, the Z gate, X gate, or a combination of both. And that is a teleportation algorithm. And I will show it now in the demo. But let me first of all also start up my environment while I am showing that. And then I will be able to join. Yeah. Just a second. So I will continue first of all here. So while my environment is starting up, the quantum teleportation algorithm, as you find on the left-hand side, is one of these traditional algorithms. I call them traditional because if you open a book on quantum computing, you will always find these fantastic algorithms that are based on the fact, on the assumption that you have a perfectly working quantum computer. And the famous one are Shor and Groover. Shor, as you know, is the cause of the quantum threat. But within the Shor algorithm, you also find some interesting techniques, such as the quantum phase estimation and the quantum Fourier transformation that are used in many other algorithms. And the Groover algorithm, of course, for the search with the quadratic speedup. The teleportation is also very useful as soon as you need to copy a quantum state from one qubit to another. On the right-hand side, you find more practical algorithms. Things like that are also taking into consideration that our current quantum computers might not be perfect yet, but there is noise on the machines. They're using hybrid approaches, and they can be combined with error mitigation and error suppression techniques if you want to run them on a large number of qubits and a relatively high circuit depth. But you see there a couple of examples like the variational quantum algorithm with the quantum approximate optimization algorithm for combinatorial problems, the variational quantum eigensolver in chemistry, quantum neural networks in quantum machine learning. It's also part of this family. Quantum support vector machines and quantum generative adversarial network. So you find some, by the way, the latter is really used to generate synthetic data. So you find really quite some interesting, I would say, evolution here. What you see typically in the second column is that these algorithms, they're a kind of basis, I would say, a pattern, but this pattern is adapted case by case, problem by problem, depending on the requirements of the problem that we want to solve. I give an example. I've been seeing already the recursive QAOA or the CVAR VQA and things like that. So adaptations of these algorithms in order to make them, I would say, applicable to a specific case. Let me now take a look to my, I hope that everything is fine and up and running here. And then I will share my screen. Yep. Just a second. Yeah. And I already opened my, and then I share my screen again with you. Just a second. Yeah. I will. Voila. I am ready. And now I will stop my sharing my screen, and I share another screen now with you. And yeah, you should see my screen here. You see quantum teleportation. And what I'm using here as a environment is what I'm using here as an environment is QBRAID. You might know that QBRAID is an environment that is supporting several quantum technologies. Why do I use it? It's running in the cloud. Of course, you have only 25 hours per month. That is relatively okay. Why it of course it allows to test. I often use it to test out new algorithms, because you can also do a local installation, and I do have it on my Conda Forge environment. I also have Visual Studio Code run locally, but you don't want to spoil sometimes your own local environment when you are trying out new things. And that is where I always like QBRAID to test out if something is going wrong. You just start up a new session, or you start up a new environment, and you are done. Okay, so let's come back to the example. As you can see, I've been installing the latest version of Qiskit here, and I will not run it again for the sake of time. I tested it already out before this session. So I have Qiskit 2.3.1. You also know that visualization allows me to visualize some results in a more readable way. I have been running this solution on the AER simulator. I could also do it on a real device and make use of noise handling techniques, but I show this now on a simulator. When the imports are not very special, I create here the protocol. You can see, equivalent to what I found on the picture, I create a qubit, the E bit of the entanglement bit 1 and 0, classical register. I create here this bell state, the inverse bell state, the measurements, and then let's say the logic. If the test is 1, I apply an X gate. If the test is 1 on the B, I apply a Z gate. And that is the protocol without being applied. Okay, then I take a specific case, and you see here I have taken a bond with square root 0.15% of defaulting and 85% of repaying. And I have the square root. Of course, when I sum up the squares of the coefficients, I get a total of 1. And that must be the case. So the state will be controlled at the moment I will allocate it to my quantum state. You see here, I allocate the initialization to the test circuit, state to be teleported, qubit. If this state would not be valid, I would get an error. It must be, it must satisfy that the sum of the squares of the coefficients is equal to 1. Then I compose, do a composition, you know, the compose, in which I combine two quantum circuits, in this case, the initialized state and the protocol I already made. Also, I add a resulting qubit. Also, let's say I add this register. Excuse me. I add one more classical register to do the measurement to test. Yeah, when I would, yeah. I would not really need to do so to add this. I just do this for educational purposes, you could say. In case I would not be curious and let's say I would believe the circuit is doing what it should do, I do not need to make this measurement, but I do it to test that it is really working. And I apply it for a different number of shots. As you can see, I've applied for 100 shots, and 100 shots, yeah, it's relatively far away. Yeah, there's some error on it. It should be 15 and 85. You see, the statistical error is relatively high. This has nothing to do with noise. This is really a statistical error. When I increase the number of shots, I see that I am already much more closer to the 1585. And when I apply 10,000 shots, yeah, you could say that even percentage-wise, I am at 85, 15% almost. Increasing the number of shots, of course, in a real device costs time, time and money. So this is often what we need to do when we work on a real device. We need to find a balance between the number of shots on one hand and the accuracy on the other hand. So, but when I would say I move this algorithm to a real device, you can already divine I need sufficient shots to be sufficiently accurate. And let's say the real noise is even not documented in this example. Okay, if there are any questions, please don't hesitate to interrupt. Or to, yeah, that's not really interrupting. So this is an example of low-level coding. Low-level coding with really the qubits, the gates. But okay, let us now go to my second part of the demo. I stop my sharing and I go to this one. Suppose I have a credit risk data set with 20 columns and the label of the risk class. I want now to predict the risk class being low, medium, or high. Yeah, I have here, you see, these are 20 rows, but don't let confuse you. Each row corresponds with a column in my spreadsheet or in my CSV dataset. And the blue ones are the ones that are numeric, first of all, and I'm going to use them to predict the risk. So I have people that have taken a loan at my bank.
Excuse me, can you hear me?
Yes, yes, I do hear you.
Excellent. So you are not sharing at the moment?
Ah, excuse me. My apologies.
Thank you. Thank you. No worries.
Do you see my screen now? My apologies. I was a little bit too fast.
Yes, now we can see it. Thank you.
Exactly. Thank you very much. Sorry for the I will I forgot. So the blue columns are really the columns that determine the label. The label is a risk class. There are 3 risk classes: low, medium, and high. And as you can see, I have 20 columns. So normally my quantum algorithm would be a good candidate to take all these columns if I would have enough qubits. But for the sake of the demo, I only take 4 columns here. You could determine these columns by principal component analysis, or you could also say, I just take here the numeric ones, 4 numeric ones. By the way, you could also convert the categorical columns, into numerical, let's say, values. But I did not do that here. I just take the 4 columns, and I would like them to use these columns to predict the risk class. What am I going to use here is quantum machine learning. And quantum machine learning, where do you position it within the world of artificial intelligence? In the traditional machine learning. Some people think that traditional machine learning is not useful anymore because we have LLMs, we have agentic AI. This is not true. So classical machine learning is still important, and deep learning. Last week, I had a call with one of my customers. I'm working in the financial services sector, and they want to improve their machine learning library. And they are looking for a tool to do so. And so this is traditional machine learning. And quantum machine learning, it's one of these areas where quantum computing can be of added value. And you might already have seen that slide. Where do we position quantum machine learning? And this is a picture I did not invent myself, to be honest. I found it in this book from Maria Schult and Francesco Petruccione. This is a book of some years old already, but if you are interested in quantum machine learning or applying quantum computers for machine learning, I certainly would recommend it. And where do we find quantum machine learning? It is really on the intersection of classical data and quantum computation, CQ. There are other combinations as well. Traditional machine learning is CC, classical data, classical computing. There is also QC, quantum data, classical computation. For instance, I have a customer who is focusing on battery recycling. They use quantum data coming from the chemical reactions to do predictions about about how to recycle the battery. Okay, but I will focus on CQ now, and I will skip some slides for the sake of time here. What we see when we compare classical machine learning on the left-hand side and quantum machine learning in the middle, the big difference is encoding, meaning you have to encode your classical representation into a quantum representation. We call that data encoding. And there we find several methods. If you would take research papers on this matter, you would find a lot of different examples. Basis encoding, amplitude encoding, angle encoding, phase, dense. These are a little bit self-made types of encoding. Within Qiskit, you also have built-in encoding methods. We call that feature maps. Where does the name come from? Yeah, it's clear, I think. In general, you take features from your, let's say, from your original data, and you are going to map them to qubits. So you map your features to qubits. That's where the name is coming from. And built in Qiskit, you have multiple approaches: the Z feature map, the ZZ, the Pauli, and the efficient SU2. The efficient SU2 is looking at the hardware itself and making that encoding as good as possible. Often you see there a combination of Hadamard gates, rotation gates, C-not gates, so entanglement and superposition. On the next slide, it's very busy, I know. In green, I've elaborated an example of basis encoding, amplitude encoding, and angle encoding, and how you do that with a very simple example. But what we see more and more is that people use the built-in feature maps. And that is what I've also been doing in my example in the next coming minutes. By the way, this is an interesting slide. How can you read that slide? If you take the right-hand side and you compare it with the left-hand side, you see much more granularity. This is a classification problem where you classify between orange and blue, and you see when you use more entanglement and superposition in your encoding or your feature map, you get higher levels of and more accurate classification, more granularity. This was already detected by a research team some years ago. You find that in this nice research paper at the bottom of the slide. So the more quantum features you use, the better the classification results. Yeah. Okay. Let me now go back to this, and then I go to my example. So, what do you find today in quantum machine learning as the most promising approaches? These are support vector machines for classification, quantum neural networks, and quantum generative adversarial networks. I will show you an example now on support vector machines. Before doing so, some small explanation. What are support vector machines? It's classifying two sets of data. You see here on the right-hand side the crosses and the circles with a hyperplane. In this case, a straight line. Why? Because we work in 2 dimensions. 2 minus 1 is 1 dimension, so you have one-dimensional structure. If you would go to 2 dimensions, you would have a hyperplane plane. If you go to 5 dimensions, you would have a 4-dimensional hyperplane to split up the two sets. And what we see is that sometimes we need to go to a higher level of dimension. I will illustrate that. I have to take a look into the timing I see. So you see here the blue and the red points, and you cannot classify them with a straight line. But when you go to a higher dimension, the 3-dimensional structure, you can really separate the blue and the red dots with a hyperplane, a 2-dimensional hyperplane. And then we can do the classification. And now comes the value of quantum. How can we bring from 2 to 3 dimensions? That is what we call the kernel trick. You develop a kernel that transforms to a higher dimension. And there now it seems that with quantum computation, you can develop kernels that are really efficient, based on the inner products of the original vectors. So we have quantum kernels that can be developed based on these inner products, and they are very efficient to do the classification. Let me show that in an example. Yep, and I close this one, and I stop sharing my screen, and I share another screen now. Again, share my screen. Yep. And I take here my example of credit risk, and you see I have an own feature map. And of course, I will not go in each and every detail. I think, please let me know what my final hour is. It 6? If it is, if I have a little bit more time than 6 o'clock, I can go until 10 minutes past 6. And then is that okay for you?
Yeah, Eric, absolutely. For us, it's okay. We can stay a little bit longer, just your timing.
Okay, good. I will take 10 minutes more than I apologize. So this is an example of a quantum kernel. And I skip some of the, what we do need to install here is Qiskit machine learning. So that is something that you need to install to do this. I also have installed scikit-learn, so the traditional data science kit, because this is a hybrid approach. We need both. This is the overlap method, I would call it, or function, whatever, the same, in this Qiskit circuit library. It is built in. It is relatively new. If you would go to quantum machine learning examples a couple of years ago, you would find a completely different approach. Unitary overlap is really it's a function that calculates the overlap between quantum states. And if they are really similar, the overlap value is 1. If they are completely different, they are equal to 0. Compare it with an inner product between vectors. Perpendicular vectors have a scalar product 0 or an inner product 0. Vectors that are, let's say, the vector with itself. When I do a scalar product of a vector with itself, it's 1 as a result. So that is a little bit the principle. So this is a function that when vectors are data points are really different, it will give you a 0. When they are really equal to each other, it gives you a 1. And then you have degrees between 0 and 1. Okay, so that is the thing what we are going to use. I have here a data set, the data set you saw in the introduction. And I have taken the first rows, and you see the duration of the loan, the amount of the credit, the age of the customer, the installment rate, giving an indication of how much has been borrowed compared to the monthly, to the yearly income. You see, for some people, it's quite high, 4 times, high risk. Yeah, and then the credit class. So this is the historical data. And you see here how we are going examining the data. This is a little bit data scientist work, very simple one. The only special thing we do here as a data scientist is normalizing the data, because you see that the ranges of the data of the different columns are really different. Really different. So what we do, we divide by the maximum value. We have the min-max scalar so that every column has the same weight in determining the risk. Then we apply our traditional train test split in machine learning. This is an example of the first 5 rows. Yeah, nothing special. We only have 120 rows, but this is a very small data set, but the principle could be done very well also for 1,000 rows or more rows. No problem at all. Only it will cost you more computation time. And I am a little bit careful. I only have 10 minutes a month, and I consume often these 10 minutes. So I made first my examples a little bit modest in size so that I don't consume too much. And when I'm sure that everything is okay, I extend to more samples. Yeah, then you have here what we call the kernel matrix. Yeah, which is initialized. What is the kernel matrix doing? This is really the kernel I already talked to you, explained to you, excuse me, discussed. And the kernel matrix is let's say, the representing the kernel with, and we are going to multiply each, let's say, data entry consisting of 4 values, 4 features with this kernel to, let's say, that, and this will allow us to predict the risk class. And this is what you find here. Before I do so, I also create a feature map. The feature map that is representing my data into the quantum circuit. And you can see I am using here a feature map that is built in. It is based on the my apologizes. No, it is the feature map. I was a little bit confused. It is the own feature map. You see, I have created my own feature map here using rotation gates with the parameter theta and RZ and RX gates with the X value. The X values are the real data. These are not parameters. These are the real data coming from my data set. You see that also here in the that I allocate these values. The theta, that is a parameter that I need to train for. So I need my, let's say, my kernel will be used to find the right value of theta. That is the parameter I need to train for. Here is the kernel matrix formed in 2 loops. This is, by the way, a new approach as well. In the past, we had an easier module. This is now an approach for the, let's say, for the matrix. We call that the training matrix with the training data. And this is the matrix for the test data. As you know, in each time we do data science, we use training data and test data to test the quality of our algorithm. And what we use then is the scikit-learn to use the pre-computed kernel. But the pre-computed kernel is calculated with a quantum computer. As you can see, it is here. We have been running our circuit with the sampler. The overlap circuit is based on our kernel and is measured. And yeah, then we are going here. When we have trained the kernel, we are really going to apply it. And we see that the score is 93%, a relatively good score. Yeah. So I continue for the sake of time. We could now try out not our own, let's say, feature map, but let us now see the example with a predefined feature map being the Z feature map. And I go a little bit lower. You see here the Z feature map is built in within Qiskit. It is another structure. It doesn't use 2 qubits, but 4 qubits. Yeah. You see, of course, an impact. There is, it is a larger circuit. There is more depth, more width. So it has an impact. It has you would see if you would run this, it takes more time. Yeah. Let us now take to the final result. For the rest, the approach is completely the same. But when we take then a look to the result, we see that the accuracy is lower. What could be now the next steps? Of course, you can play around with other feature maps. You could say, I use the ZZ feature map, the efficient SU2 feature map. I use other data to train. Yeah, there are multiple approaches I increase the number of repetitions here. So there are multiple ways to review your work and to potentially improve the work. Of course, this is really data scientist work, just like before. Okay. For the sake of time, if you don't mind, I go to my final introduction. And this is about the VQA. And perhaps I will show very shortly a slide and then show the demo immediately. Before I continue, one interesting remark. Let me show you this one. What do we see? What do we expect from quantum machine learning and quantum support vector machines specifically? That is that this type of data sets, what do I mean by that? A lot of features and the number of data is relatively modest, we see good results. So we would say when you increase the number of features and you increase, but the data is relatively modest, you still will have a good prediction. That is what we see typically as a promise by quantum machine learning models in quantum support vector machines, excuse me. Okay, let me now go to my final example, and this is the following. We have here what we call the max cut problem. The max cut problem is a problem that you find in many industries, also in finance. You see here a very simple example. What is the goal of max cut? You're going to split up a graph. It is in the graph theory, which is coming back a lot of times in optimization problems. And you have multiple optimization problems. Think about the traveling salesman problem, the knapsack problem, but also the maximum coloring problem and things like that, but also the max cut. What is a max cut? You want to split up your graph in 2 subsets of nodes with a maximum number of connections or edges. You see here the edges are in red, the nodes are in white or black, and you see we have 2 sets, the black set and the white set, And you could verify that they are split up by a maximum number of edges or connections. Where is this used? Yes, give an example. Suppose I have, I want in the financial services sector, I have different types of, let's say, investment types, but I want that the investments that I put in one basket have the lowest dependency that is possible. Why? Because I want to minimize my risk. Suppose I have a share that is strongly influenced by another share, like the white and the black here. So if the share of IBM increases, perhaps also the share of a competitor is increasing. I don't know, because the IT climate is very well. I want to avoid that because I want to diversify in my portfolio. I want independent investments to spread the risk. And so I see that the white ones don't have any connection. And also the black ones have a minimum number of connections. I want that situation. That is what we call the max cut problem. And the max cut problem, I have here an example. Again, in a bank, I have 4 possible portfolios of investments. And I have weights, a high correlation and a low correlation. I don't want a portfolio of investment P0 and P1 because they have a strong correlation. So if I lose a lot of money with P0, I will also lose a lot of money with P1. P0 and P2 have a low correlation. If I lose a lot of money with P0, not necessarily with P2. So I still am not that bankrupt. And that is what we try to do here. And what we use is a variational quantum algorithm. A variational quantum algorithms, you find them in combinatorial optimization, what we are going to do here, QAOA. You find them also in machine learning and also in chemistry, variational quantum eigensolver. We are going to do QAOA. And how does it typically work? It typically works in a loop. It's a kind of, you're going to represent on the left-hand side, your, let's say, you are going to create what we call an ansatz. This is really the space where your solution can be found in, can navigate in. It's often represented, it is represented by a parameterized circuit. You have a parameter that can surf around in the space, and you have multiple possible solutions. Okay, then you will, of course, transpile it and you will measure it. And then that measurement is a measurement of an observable. You are going then to calculate a cost function on a classical computer. The goal is then to adapt the parameter in such a way that your cost function converges to 0. And the cost function is, let's say, representing an objective. For instance, minimizing cost can be maximizing return. Minimizing the energy state. Minimizing losses and so on. So, and you're going in a loop, you're going to adapt your parameter step by step to minimize your cost. That is what the VQA is doing. And in the max cut challenge is a specific problem that is solved with a flavor of VQA being the quantum approximate optimization algorithm. I want to show you the demo now as a final part in my, let's say, in my presentation. And I will go to my, QBrate environment again. I will close this example and this also, and I go to my VQA. I have elaborated this in a very simple way because that makes it understandable. Let me show the code. First of all, I've been using RustWorks to generate, to define, I defined myself this small graph. You see 4 nodes, 5 edges and weights. They represent investments. Let's say a investment with number 0, 1, 2, and 3. And you see high correlation between 2 and 3, meaning that, yeah, I want to avoid this to be in the same portfolio, because if 2 is the shares of 2 are decreasing, yeah, the shares of 3 as well, of course. And then I have the mathematical representation of the max cut problem. The key thing to understand in this, and it's very easy to understand, the only thing that you need to understand here is that this cost function contains xi multiplied by 1 minus xj. And how do you need to understand this? Well, if we have, if the xi is equal to 1, when a node belongs to subset 1, and the xy is 0 when it belongs to an other subset. What we want to maximize is this multiplication. Why? Because if xy is equal to 1, we want the other to be 0, so that xi, xj are not belonging to the same subset, but are belonging to a different subset of nodes. That's a little bit the key to understand in the mathematical representation. The wij are the weights, and the rest is relatively simple. At the given moment in time, we represent the z by z gates, because they can have an eigenvalue 1 or 0, and then we apply it. What you see here is the ansatz is QAOA ansatz. This is built in within Qiskit, so I don't need to program this ansatz myself. What I've done here is just decomposing the circuit and making a drawing of it. And you see, this is done by Qiskit itself. I did not create that myself. Qiskit gave this to me. The cost function is calculated. And you see here also the calculation using the ansatz, the Hamiltonian and the parameters. The Hamiltonian is this one, IIZZ. Where is that coming from? Yeah, this is really representing our graph. Let me give a look here. You see here the connections, you find them in this Z Pauli. You see here, for instance, I take 1, ZZ. It means a connection between the qubit Q2 and Q3. Qubit Q2 and Q3. When I have here a ZYYZ, this is a connection between qubit Q0 and qubit Q3. So the lines are represented in the Pauli operators, to make a long story short. And then I run it and I do the optimization with the Kobila optimizer. You have multiple types of optimizer, gradient free, and the optimizers using gradients. What is the difference? The gradient free optimizers are sometimes a little bit slower, but better resistance to noise. The gradient-based optimizers are faster, but more subject to noise. So if you have a noisy current quantum computer, so the Kobila optimizer is used in when you have a noisy environment, for instance. And I am at the end. So indeed, and when I go to the end of my example, I see that the green ones are put in the same portfolio and the red ones as well. I could have done it manually as well. I see it. The 0.8 and the 0.9 are forcing my 3 and my 2 in different portfolios. And the 0.6 also. And the 0.3 is a low coefficient. So that is a little bit an example of VQA and quantum approximate optimization algorithm.
Thank you so much, Eric. Thank you so much. You deserve an applause. Thank you so much.